sched frequency governor, which basically ties the scheduler in with the frequency, CPU frequency governor. Sched tune, which is the boosting mechanism. I guess one area that's a little newer than the original 5.2 patch set is the using Walt instead of Pelt, and there was a talk on this yesterday. And then you also need an energy model for the board. I'm not going to cover this. Leo's covered this in great detail in previous connects, so you can see the slides, links in the slides before. On the kernel side, you basically just need to set these config options. This is kind of some just how-to sort of things that you'll need to enable. I'm not going to go over these in details, but you can look at this later if you're interested. As far as the kind of components involved, so I'm going to go over a little bit of basic concepts and then kind of talk about the different components that are involved in this, and also give kind of more of a background on how Android handles these components. So Android has a handful of conceptual task types. And so you have the top app, which is basically what is the active app that the user's using right now. If that's a split screen view, it's the one that's most recently touched. This is new and N. Then we have foreground, which is basically anything else that's in the foreground that the user might be interacting with, but not most immediately. There's the background tasks. These are other applications that just haven't been used. They're still in memory, but they're running in the background. System tasks that are similar to background tasks but are core to the Android system. And then the audio app and audio sys, those are basically the same as foreground except for they run with real-time priority. So that's basic types. The activity manager and sched policy. So the activity manager is the bit of code in the framework that tracks kind of these foreground and background tasks and moving and basically tracks moving them between those task types. It also adjusts things like the timer slack. And then the sched policy code is the thing that actually manages the low-level details of when they move between those task type states, how they'll change different C groups in order to, I guess, get into the right place. Now Android has a couple of different kind of, it's almost like redundant approaches that they use. So there's the base scheduler behavior, which, this is something that EAS affects. And kind of how it does its task packing and dealing with the different asynchronous SMP. The CPU sets basically force the processes, so this is where Android has a little bit more of an opinion about where it wants different tasks to run. So basically CPU sets are sort of like guardrails on the scheduler. And so it kind of keeps tasks to specific CPUs as designated. CPU control kind of increases that further and pushes it down to what portion of a CPU that a group can run. And then there's sched tune boosting, which allows various groups to be given kind of a default boost so they'll run faster. And then interactive touch boosting, which further can boost those tasks. As far as, again, the nuts and bolts, you can go into your device's board config. You'll want to enable enable CPU sets to true and enable sched boost. One caveat is there's this enable sched underbar boost. Very confusing. This is basically, I would consider kind of a deprecated foreground boosting that was used for some of these big little HMP-based systems in the past. So you can run across code, and we'll kind of touch on this as I go through in case people see this and get confused, but I'll try to make it clear that these are things that you don't want to be doing in current devices.
Something we're going to add to the common device, right?
No. Pardon? Yeah. Okay.
Something we're going to add to the common, well, CPU sets, I think we could make runtime.
Okay.
So we could add this configuration.
Well, so some of these are set to, yeah, I mean, I guess that's true. We could add these generic options. Some of these you do want to have this option enabled as true because it changes the Java code and how it manages the different groups. So again, yeah, the CPU sets, this is what limits what processes run where. Again, there's a number of different C groups. There's a little, I apologize for this one little kind of complexity here. So there's going to be C groups that are named similar things to Android task types, but they are not always a one-to-one mapping. In this case, it is pretty straightforward, one-to-one. So in the CPU sets, there's the top app again, there's the foreground C group, there's the background C group, the system background, which is for the system tasks, and then again that foreground boost, which is deprecated. Don't just kind of ignore it, but in case you see it. An easy way to kind of see this and how it's kind of used, this is kind of a theoretical example, 4 cores, 2 littles, 2 bigs. You can easily just set all background tasks are basically limited to 1 little core. That kind of keeps them out of the way. Whereas for the foreground tasks, you might give them most of the cores. And then you can limit the system background to maybe just the little cores. You'll see sometimes in these foreground boost cases, they'll basically pin them to just a big core, to a couple big cores, so that they get kind of more consistent performance. And then finally, top app, which would get, as all the CPUs. So here's kind of a concrete example that we used in HighKey. It's basically very similar to that example, where basically we say, okay, on an 8-core system, we'll give the foreground basically the top 7 cores. Top app will get all 8. The background we just pin to 1, and the system background will get the bottom 4. But if you go look at something more complicated like the Nexus 5, this is one of those cases where, so they say it's a 6-core, so you've got 4 little and 2 big, I believe. And in this case, you say, okay, the foreground's going to get all but 1 of the littles. And so then the top app will get everything. And so that kind of reserves 1 of the littles for the top apps. You'll see the foreground boost gets the big CPUs. The backgrounds just gets 1 small CPU, and then the system background get 3 of the little CPUs. Now CPU control, this is another C group tool that basically limits the amount of CPU time a task can get in that C group. So this is something that can be used to further restrict the amount of time. So not only can background tasks only run on 1 CPU, but they can only have a little bit of that CPU. And so if you go look at the common initRC, it basically sets this up for all systems. And you can see there that basically down at the bottom, there's the, it's setting up basically that you can have 5% of that 1 CPU that you'd be using. It also affects real-time tasks, so you can see in the bold, there's normally real-time tasks get throttled at about 80% of the CPU time. And for the background non-interactive tasks, there's throttled further to 70. Now, go ahead. So it tends to be, because it depends on how you set up the C groups or the CPU sets.
So here,
but
use this as example. How can I check what CPU is used for this background?
So you'd have to look at how it's set up for the device-specific config. And so, for example, for the Nexus 5, the background tasks just get 1 little core. But that could be on other systems, you might have 2 little cores. So it really varies. And so it's one of those things where there's no prescription that says what the exact.
Yeah, just use this example. The CPU time set in the next slide is limited to the CPU core 0.
So this one, it's a separate C group controller. And so basically it says that tasks in that C group are limited to 5% of any CPU's usage, or CPU time.
CPU.
And so if you had 2 CPUs, between the 2 CPUs, it could use 5% of those shares. So this is just a CPU time restriction.
This is
But
on all CPUs or on some specific CPUs.
Say that again?
Like this limit is set on the CPU core 0 or on all CPU cores.
Is it set on 1 CPU or is it set on all the CPUs?
So as a C group is across all the CPUs, but then the tasks that are in the background non-interactive tend to be in the normal background. So they tend to be stuck on just the 1 CPU. But it's not, it's a separate C group controller, so you can have multiple CPUs that are limited to a certain amount of CPU time. Or not a certain, you can have multiple tasks that are limited to the CPU time that are able to run on multiple CPUs. It's I'm sorry. But yeah, they're independent C group controllers.
Can this be done later in the RC brackets after the system?
I would believe so. I don't see a reason why it wouldn't. I don't believe, I mean, yeah. So.
We do a lot of experimentation in various groups playing around with these settings, right, at one time.
All right. So the next kind of C group that controller that gets used is SCED-tune, and so this is basically this runtime boost knob. Again, I didn't really want to get into much details about how EAS works, but to try to explain this, basically what this does is you have kind of two different hooks. So there's a system-wide SCED CFS boost in sysfs, and then you can also have a per C group SCED-tune.boost for this. And basically what this does is it adds kind of a percent margin or a weight to the tasks. And so basically any task that's in that C group is going to seem like it's a bigger task. So when EAS is doing its task packing or its CPU frequency selection, it's more likely that you're going to be running on it's more likely that the CPU frequency will be ramped up or you'll be moved to a free CPU. So this basically is a way to kind of just improve the performance that those tasks will see, even though they may not be quite as heavyweight. For the SCED-tune C group, there's foreground, but again, this is where that kind of, there's that aliasing between the C groups and the task types. Foreground also includes top app here, so it's a little confusing, but just when you're looking at the C group names, that's that. And then everything else is just in the generic. And so if you look at how the S-tune config is for high key, basically there's kind of the two cases here. We have the foreground SCED-tune boost that we set to a 10%. That's not tuned in any way. You'll have to find your own magic number for that, for your own device. And then we also set for just, everything else, it's boosted to 0. Now, for the next kind of item, the next component that gets involved here is the Android Power HAL. And so this is something that provides a number of different signals from user space to kind of tell the device kind of what the system's doing and how to behave. There's a number of different signals or hints, I guess, it can get. We're really going to only focus on the power hint interaction. The one little note that I had was that down at the bottom there's these power hint video encode and decode, and if you look at the kernel source, it says that these are to be deprecated in, I believe, Keylime Pi, which is, I think, was the precursor name for KitKat. But they apparently are still in use, so I assume that you wouldn't implement something for this, but you may actually want to. We're just going to focus on the interaction one. For the old interactive CPU frequency governor, when you were implementing a power HAL, it was fairly straightforward. There was basically an initialization setup where you would set a lot of different tuning knobs, and then you would set this boost pulse duration, which would say how long after a touch event you would want the CPU speed to kind of be bumped up. And so you could say, okay, echo a second into this boost pulse duration. And then when the device, or when user space gave this power hint interaction, you could then just simply echo 1 into this boost pulse flag. And that would ramp the system time, or the CPU speeds up for that 1 second. With EAS, it's a little bit different because the kernel doesn't do the deboosting for you. So it's not going to lower that speed. So you can echo, basically on power hit interaction, it's easy to echo, we'll say, okay, let's give it a 40% boost for, the foreground tasks. But then it's up to the power HAL to wait some specified amount of time and then deboost it back down. So this makes the implementation a little more complex. It's not super difficult, but I've got an example here. This is too small to read, but the source is up there. It basically ends up being a semaphore signaled thread that will sleep for the time that's needed before it drops the boosting. But so it's pretty straightforward, but not exactly trivial to implement. It took me a little bit longer than I would have thought. Some other conceptual complications that we talked, or that Yuri's talk covered, is negative boosting. And so this is a case where, and this, I'm not sure how much this will end up maybe duplicating some of the CPU control, where you're trying to kind of reduce the amount of time that a process has. This basically would lower the weight for tasks so that you're more likely to be packed onto a single CPU. So you're going to seem like you're a smaller task, or the CPU frequency won't be increased for your behalf. And so this is a way to kind of further kind of get those background tasks to become less, have less effect on the system. I haven't done anything to implement any of that, so it's one of those things where it's something you might want to keep aware of and kind of start looking into. There's also this prefer idle, and this is basically when it tells EAS that when selecting a CPU for a certain C group, you'd want to push the tasks to an idle CPU rather than trying to pack it onto a CPU that has enough capacity but might be doing something else at the moment. And so this basically gives a little bit more responsiveness, it costs more power, but it's something that you might want to consider for the foreground SCED-tune group. And that's something we turned on for Heike. That's it for me. If there's any questions, but big thank you to everybody on the ARM team that was helpful for this, as well as Leon's. I just kind of put together a lot of things, so I was writing on a lot of coattails with this one. So.
Yeah, actually, I have a question. One challenge for the JIT system on the Android is that many JIT systems actually have a separate compiler thread which does dynamic compilation, and this thread would seem to be not so busy on Android, but the performance of this JIT thread compiler thread is critical to the whole Android performance, because while the JIT thread is doing the compilation, the application thread has to run in interpretation mode to wait for the JIT thread to finish compilation. Mm-hmm. So, but for traditional kernel scheduler, you cannot see such behavior. So sometimes you just schedule the JIT compiler thread to the small call, so it takes a long time to finish compilation. So I don't know if the EAS scheduler can handle this situation better, or does it provide any interface for the application to do any boost? Okay,
yeah, that makes it sound like maybe with the system, I assume that this would be a task that would be categorized as system background. And so it might be able to, increasing the C group set for system background might improve the performance there. EAS is going to do its own task selection inside of that C group, so after the CPU controls kind of say what CPUs that EAS can decide to put this task in. So EAS still has an effect on that, but it may need it needs more options for that. I'm not sure.
We use one of these tools.
I'm sorry?
We use one of the tools that you mentioned. This is a thread that idles for most of the times, but when it runs, it should run on the biggest, fastest CPU.
So some of the hints are just predetermined, like, so that's part of the system interface. So I don't know if abusing the existing hints would be the right solution.
So I would just say on this that, I mean, this is highly tuned on the device that we did the work on that hasn't come out yet. And this didn't pop up as an issue. There was a lot of tuning of ART and JIT compiler, and we did not need to do any special casing for it. So it didn't get on the radar screen, or we would have done some special stuff.
Anything else? Yep.
Just now you have set some the boost value for example for the Heike platform. So question is that usually for the specific platform, how it can figure out what the boost value is best for the platform. So maybe we need to get some testing case. We can get to know, maybe for example, for the foreground or top app, then you can get a specific level. This will be enough. So how to define this or how to decide that?
So this is the default boost value for foreground here. That's what you're talking about. So what we did for that one was we sort of developed our baseline using a workload that we wanted to have pretty low power consumption, but that would be running as a top app. So we actually used some video streaming. We used YouTube and a couple other things, and we were working towards the highest boost value that kept us the power within our acceptable limits, and then that boost value then goes and helps you in other heavier workloads, performance-wise. So that was what we did.
It's one of those things where ES does have sort of a simpler interface for the, there's one knob, and you know, most of the, I guess, tuning really has to be as part of the energy model, but there is sort of at least a theoretical sort of scientific way to define that. So it is nicer than the interactive governor, which had a ton of knobs, and you had to figure out.
Yeah, and the really cool thing is you have this explicit knob where you are directly trading off performance and power. So you can say, okay, I want better power characteristics, turn it down.
The difficult part is, of course, per device that needs to be tuned. And so it's one of those things, and part of this comes from just the fact that we don't have a way of expressing, short of something like the deadline scheduler, but at that point you've got to rework all of user space to make use of that, to really define kind of what the performance behavior you want for that workload to be in a certain amount of time. So you're going to have to fudge it for every device.
And then some of the work we're planning to do has to do with recognizing different workloads and then tuning this differently as we recognize workloads. So a year from now when we're talking, we'll probably be talking about some of those specific workloads that we've tuned.
So I've done some experimenting with the CPU set myself, and I remember that some kernel threads are not affected by that setting at all. So I was wondering, when you said when you limit the CPU time for background tasks, does that affect kernel threads as well?
I don't believe that those aren't, the kernel threads shouldn't be in the C group. And so they're going to be in the default C group, and that doesn't have any restriction on it. There is the setup that it does where it does set the throttling at 80% for real-time tasks. And so that's a knob that does affect everybody, but that's just kind of a safety issue because you don't want real-time tasks to just run away with the system.
Okay.
All right, going. I'm back. So the other kind of change coming down the pipe that I wanted to talk about was the sync API changes in 4.6 and newer kernels. So basically the Android Sync API and staging, it's been refactored, pulled mostly out of staging into the DRM fences and this new sync file code. Gustavo Paravan has been doing this work at Calabra, so I really think big credit to him. It's a lot of awesome work. Oh, right, okay. Well, in 4.9 maybe it'll be completely out. I haven't seen that land yet, so I will wait and see. So this is good news. It's great news. We've got a proper sync fence API in the upstream kernel. This is being shared across a whole bunch of different platforms. It's one less Android-specific kernel feature. This is really, really, really awesome. I'm super excited. One less thing to keep in the Android tree. The bad news is if you have an out-of-tree vendor driver, it's broken, and it's probably broken pretty badly. So I want to give some credit. So back at the 2013 Linux Plumbers Android MicroConf, Eric Gilling from, at the time, Google, came and gave a talk about this Android Sync interface and kind of used this chart-style diagram to explain it. And comically, in every talk about Android Sync, everybody redoes these things. So in that tradition, I will provide these same examples. And so basically, in the Android Sync concept, you have this thing called a timeline, and this is basically just kind of gives a kind of a count of different incremental events that are going on. And you're able to put this sync point at some point along that, and basically that sync point will fire or expire when the sync timeline has moved to that value. You can have multiple timelines for different parts of a driver or different devices, and you can have sync points on different timelines. And then there's basically this sync fence, which was kind of an object that got pushed out to user space, and it could contain one or multiple sync points, and those sync points didn't have to be on the same sync timeline. Now moving over to the DRM fences, it's sort of like Bizarro World, where everything's similar, but it's named differently in a confusing way. And so now instead of the timeline, we have a context. Instead of the sync fence, there's a sync file, and instead of the sync point, there's a fence. So it's a little tough to get your head around sometimes. I tried to go through and create kind of this nice translation table so that folks who are trying to go through this could easily try to figure out, okay, if I'm looking for the config sync, it's really, you need config sync file now, and if you're talking about a sync fence, you want the sync file and various functions that are very similar across the two APIs. But the problem is that this is a mechanical translation. And with a lot of mechanical translations, it really just, there aren't direct matches. And so we run into the case where, there were a lot of async wait functions that were previously done on sync fences, and this is all inside of the kernel. The sync fences are closest to the sync files, but now those async callbacks are all done on fences, which were analogous to the sync points. And so the mappings just don't apply right. It's just not a one-to-one mapping. Also, the sync timelines were these objects, but the contexts in the DRM world are just a 64-bit ID. So you can look at two fences and see that they have the same context and know that they're on the same, what was previously known as a timeline. And so this is, you basically have to manage your own context objects to keep track of things. Adding to this, most drivers have their own mid-level sort of abstraction for all of this, so they have their own crazy names for all of these different objects. Looking at things like the Mali, you've got the Mali timeline and the Mali timeline point and the Mali timeline fence. And that just kind of adds more confusion when you're trying to rework a driver. It's one of those things where are you going to rename, trying to remember what a Mali timeline fence is something different than, the Mali timeline point previously if you're dealing with the timeline point now points to fences. It gets very confusing. And when you look at some of the functions like the Mali timeline sync fence create and add tracker, trying to translate that into this new world is very, very difficult. So additional bonus is that a lot of this has been in flight, so there's still code that's coming in. I took the Mali driver I was working with Hikey. When 4.6 landed and things broke, I went in, tried to get it working. Moved to 4.7, broke again, had to go in, try to rework it to get it working. Moved to 4.8, it broke again, I gave up. So this is a little bit frustrating. So good luck rewriting your driver. It would be nice if you got your code upstream, then the community could help with this. It's tough. I'm kind of intending, to scare you a little bit with this because 4.9 is coming. It's one of those things where I'm hoping to scare folks to action. Because it's not just coming, it's here. I think the merge window opens on Monday. So please, please, please update your drivers, get them running against 4.9 so that we can have devices running the current long-term stable kernel. It would be very nice. And I think that's it. There's some, Gustavo has the user space lib sync changes that makes Android work with the new sync fences, and Rob's DRM hardware composer changes are there, which I've been using to test with other devices.
There's nothing specific for the sync. There's no changes to the DRM hardware.
Oh, okay. I thought it was exposing enough of it was using the sync driver.
So the hardware composer is kind of broken, and that it doesn't really use all the features in the DRM hardware.
Oh.
And it doesn't really need the sync at all.
Oh. Well, anyway, so Gustavo's code is there. And then there's a bunch of references to Eric Gilling's original talk and then all of the other talks that include his drawing. So that's, I think, it for me. Thanks. Any questions? Probably not much. It's just there you go. Boo, do something. That's true, yeah. So hopefully we'll see the lip sync changes land. That's correct, yeah. The lip sync change works with both APIs, so you don't have to worry about what.
There's one issue is that the software's timeline is a debugfs feature now. And so wouldn't really use it in production.
Yeah, that's probably true. We got to get moving. So thank you.
Okay, so Ion. So part of the Ion has kind of stalled and languished for a while, and I think part of the reason is that it doesn't really have a good driving force, and it's not clear exactly what it's being used for. So I'm kind of intending this to be a discussion to try and figure out exactly what people are using Ion for and as a path to move things forward. If you were in the status report yesterday, Tuesday, one of those days, I talked a little bit about Ion sort of going 2 steps forward, 1.5 steps back. And even here, I think some of the status I gave isn't quite up to date because people had feedback. So I guess probably the first question is that I know it's used on some narrow uses, but are you actually using Ion at all? And does anyone actually want to use Ion on mainline? Okay, maybe I should start with the first poll. Who actually cares about Ion in this room? Okay. Okay, I mean, this is sort of a useful thing, and I'm also going to present this as sort of the problem is that I'd also, perhaps this is something I'd like Linaro to help out a little bit more, is that it honestly seems to me like there isn't a lot of interest in Ion, and I'm wondering exactly then why are we spending resources to try and keep looking at it, and should we just delete it?
In the Android world, it seems like a thing that everybody just does and uses. I don't think they're very passionate necessarily about it, but it's one of those things as far as so from high key at least, we're able to use the dummy heaps successfully. So we're happy with what is already in staging.
So using it for what though?
The graphics buffers, I believe, so yeah. Yeah.
I think lots of vendors using the Ion to implement their Gall. The Gall is required by Android, so this is one of the main usage of Ion, in my understanding. Yeah.
Okay, so that's true. So yeah, that's why I agree with that, and that's also my understanding. But then, who is actually interested in trying to get Ion to run on something resembling mainline? Because again, it seems like there's been a lot of work on DRM, hardware composer type things, but not a lot of interest in sort of trying to move Ion forward. Is it that people don't actually care, or that nobody's actually tried to push this forward?
So we're not using it for any DRM-based solution. There is the issue of whether there needs to be a central allocator or not. And then the question is whether that would be Ion or a derivative of Ion.
So I'm at the point where I think Ion as it stands today should not exist. It should really just be deleted and rewritten from scratch based on my attempts to try and move things forward and then conversations with people. I agree that I think there is a need for a central allocator. It may end up being something Ion-esque, but not actually Ion.
So the way I think this is going to end up going is a central allocator API in user space that can sit on top of multiple different devices. So I guess that sounds a little bit like Gralloc, but there may be cases where you still need Ion as a potential device that you can go down to the kernel to allocate from. I know a lot of people are abusing the DRM KMS dumb buffer alloc right now, but there are cases where that won't necessarily work, such as outside the surface flinger process. If you need to allocate a buffer that could be passed and potentially put up on the display from a different process, I think currently people just hack around that with some small kernel changes. I don't know, I mean, there might be a need for Ion as just the fill in the last remaining gaps for certain use cases sort of thing.
Okay, so part of this is also figuring out which parts of Ion are actually feasible to try and pull out, just because the abusing of the DMA sync APIs for cache synchronization has basically gone nowhere. I tried pulling the cache operations into Ion. I got told not to do that, make them generic. I tried to make them generic. I got told to pull them into Ion. So I'm basically concluding is that trying to have them at all in Ion is not actually a good idea, which is going to break some fundamental assumptions. So I guess it's sort of a question about how much of Ion's existing behavior do we want to keep and say, just go ahead and say that it needs to be re-implemented, just because I think part of it is that a lot of Ion's behavior, especially with the implicit cache synchronization, happened before DMA buff, for example, was around, so we didn't have good sync points to be able to say, do things like actually call DMA map and be able to do cache synchronization that way. So really what I'd like to propose is perhaps starting a fork of Ion to actually be a central allocator and then work that into have that be useful for Grelloc. But one concern I have is that, again, going back to the who's actually interested in this, is that it's going to be written, but then it's not actually going to be used at all, and we're going to have this to have done this work, and it's not actually going to be beneficial. So, is there actually enough interest in trying to move this forward, I guess, or should we just let Ion languish and fill in line if necessary?
I mean, I kind of suspect there'll be some use cases Android has to care about that upstream mostly wants to pretend don't exist, like secure playback and stuff, and Ion might be useful for that. As far as cache flush stuff, can you just rip that all out and use the DMA buff stuff now that we've started adding ioctals on that?
Yeah, so that's what I sort of was experimenting with, at least. The problem is that there's the allocation paths, for example, they assumed cache versus uncached buffers and tried to do that implicitly, and basically trying to do the mapping and allocation time before we actually know what device is there doesn't actually work. And maybe part of this means going back to the senalloc proposal and trying to bring that back, and therefore delaying the allocation until we actually know where it's going for, and therefore we will be able to properly do the map or cache synchronization there.
Yeah, I mean, I think what we will end up with is more of a user space senalloc, so like a common API where you have instances of for all the different devices participating and sharing, and figure out at that level in user space which actual kernel device you go down to, rather than a central kernel level device allocator.
So is this, say, something closer to different, I don't actually know as much about the DRM framework, but my understanding is it sounds like you're talking about the different DRM nodes in user space and then choosing that, or is
It could be. I mean, the DRM, or more specifically your GL or Vulkan driver is one participant in that, but there's also V4L, decoders, cameras, whatever other. I was kind of looking at Ion as one particular additional device that you could share with that could allocate anything and doesn't otherwise impose restrictions.
Okay.
But yeah, I mean, the idea is more of a user space level API that is device agnostic, and you can have implementations of that interface for, for Molly, for Mesa, for V4L, whatever. So in a sense, it's a central allocator, but it's a user space API level thing that sits on top of however many different actual kernel devices, and yeah.
Yeah, okay, so this actually sort of leads into another question I had, is that in terms of trying to move things out, Ion had a set of kernel APIs, but does anyone actually see any need for any sort of Ion whatever underscore, or should the direction we move into just be Ion, whatever form Ion of the future takes, it's basically just a user space interface, and everything else should be DMA buff. This is what I'm thinking, is that there should be no need for Ion-specific APIs in the kernel, and everything else should just be a DMA buff. I guess the one use case I haven't been able to think of or be able to match up, for example, is you have an Ion heap, and you want to allocate from that in the kernel, and then send that up to user space, sort of the reverse. And from there, you would need some sort of Ion alloc wrapper. That's the only thing I've been able to think of.
I mean, hypothetically, just use the DMA buff APIs if, some special cases like secure buffers end up getting allocated from user space by Ion and then imported into the different drivers. I mean,
it's more the reverse of kernel drivers needing to allocate an Ion buffer and then send it up to user space, perhaps for IPC or whatever. So.
Yeah, I mean, as much as possible, I'd like to be able to use your driver without having to enable Ion in the kernel.
I agree completely, but I guess it's sort of a question of how much desire is this actually just a theoretical problem that I've seen in the past and probably isn't actually relevant, or are we going to run into this?
It seems like the main use case right now is for binary drivers to have an allocator. I mean, Molly is using it as its allocator, and
okay.
I mean, besides the secure buff, but there is some work to do secure buffer allocation as well.
Yeah,
right?
so I did talk with people who were doing secure allocator. I think we basically concluded is that, again, the idea of the centralized allocator came up, and that is a good case for, I think, trying to keep Ion around, which sort of goes to just reading what I had there for notes. Are there any other out-of-tree Ion features that are actually being used regularly and want to possibly get in? I'm kind of proposing a sort of a moratorium on trying to add anything to the current Ion until we can actually come up with a coherent plan to try and move it forward. But just for general reference about stuff that may be missing, is there anything major that's being done out of tree that's not in the Qualcomm tree that I already probably know about and am at fault for that is being used?
The one implementation I saw, I think, was mainly cache-related flushing, and
yeah, was that outside the Qualcomm? Was that not in the Qualcomm tree, or was it the Qualcomm tree?
not Qualcomm.
Okay.
Maybe they copied it from Qualcomm.
It's entirely possible they took that approach. So the cache APIs then are the only thing I'm at least hearing right now.
So one thing we're doing in ARM is actually implementing new Ion heaps to support like large pages, like 2 MB pages, because we have devices which can't handle 4 KB pages, and you don't want to have like large physical consecutive buffers either. So we like use 2 MB buffers with our displayed drivers, but because they need it when they sit behind an IOMMU, and you can't use 4 KB pages along with the IOMMU. It doesn't have enough TLB entries.
Okay, that's good to know. Okay, and also finally, at least I haven't. Oh, did you want to?
I was just saying, we discussed more about it in the LNG hacking group, because we still have more than 60 slides to go through, and less than 40 minutes.
Okay, yeah, I'm almost done. Just one last thing is I guess as far as suggestions for a good platform for testing, I guess, is what's the most complete open source Ion implementation I can actually use to test things on, just because I've been using the high key nominal leaf, which has a nominal implementation, but I don't know if that's as complete. Does anyone have another suggestion about things to try and use, or for example, requests of things you think that would be useful to try and find a lot of exciting cases?
The hard part is those will all be proprietary.
Yeah, okay.
High keys are
Yep, okay. So yeah, so I'll help speed this along, so thanks.
Okay, we are running a little behind schedule, so let's speed up through the next things a little bit. Next thing we wanted to talk about is reducing boot up time. AOSP is increasingly being used in environments where it is much more important that the system comes up quickly. And, we'd like to get some input on what we should be doing to reduce those boot up times. Let's go quickly over numbers we have taken about where we currently spend time in boot up.
Here we check the boot time from the total perspective. The first part take the most of time is from the surface started to the UI displayed to the home screen displayed. It takes 65%, and the second part is the kernel boot time. It takes about 26. Okay, next slide. And we measured the time from the logcat events buffer, and from there we can see that there are 5 tops to take 77% from the in total. Here the total is the Android boot time from the Surface Fling start to home screen displayed. In them, the preload part and the package scan part takes most of the time. Okay, nice.
So what are these things? These are like library reloading? What are the components there? What are those functions?
You mean the preload start?
Yeah.
Oh, that's the keyword in the logcat. Here from like the first item from preload start to preload end. This is the part to preload the DEX APK applications. Here list what we do to get the boot time. Like to get the kernel boot time, we calculate we get the time information from the message log. But here we have the problem to check the time for the bootloader, and need to get the bootloader time, we may need some other extra tool. For Android boot time, before the Surface started, we use the information from the message and use some extra information from boot chart as check. And for the details of the Android boot time, we check the time information in logcat, both from the main buffer and the events buffer. Here we not check other times like the boot application or boot some media, video or audio application. Here, just some brainstorm, like I want to get more suggestions on how to, or which part we should focus on to reduce the boot up time. We suspend some options we list here, like suspend the disk to the disk, or make the init more parallel, or use some batch file system to make the boot faster.
Well, how parallel is the init? Do we chart show that, like per port?
Not that much.
Usually boot time reduction is that and doing less.
Yeah, one of the ideas was launching some extra services like audio cleaner and so on only after the UI is up. But might be some latency issues.
So I was going to go for another suggestions is at least one thing that's been discussed before is that especially as memory sizes grow, you spend a lot of time just initializing and then freeing individual pages where you may not actually need that much more memory. So for example, on very large systems, there's now deferred struct page initialization, which is designed for very large systems. But I've seen the same effect before, reporting out that you may not need it. For example, a full 2 megabytes, or excuse me, 2 gigabytes worth of memory to boot up. And if you could somehow initialize and then defer a smaller subset, that could actually save you some significant time. So perhaps looking into the existing deferred struct page initialization and somehow expanding that for more mobile use cases versus very large systems. Just a thought.
Do we have anything else on boot up time?
I just have one thought about this, and it's not a question necessarily to be answered, but it seems like you have to think about what the use case is. So on one hand, you may want to have a fast boot time from a user's perspective, you want their perception to be that it's booted fast by giving a UI, but no services are running. On the other hand, you might have a system where the tuner needs to start playing music 2 seconds after you turn the key, but the UI doesn't necessarily need to do much. So the application, I think, is very important in deciding which area to go down.
Yeah, there's a couple of things that will probably have in every use case, like not really starting up the system, but actually loading an image from a suspended disk snapshot. But obviously that comes with its own share of problems.
Yeah.
Okay, next thing that we want to quickly go over is maintaining out-of-tree patches in user space. Fortunately, on the kernel side, there's the number of out-of-tree patches is constantly going down. On the user space side, we are not that lucky because sometimes patches just sit in the Garrett queue forever. Essentially, right now we have 2 systems of tracking patches. One is just maintaining them in our own Git repositories. One is having a patch set file that makes it easier for some vendors who are not so familiar with Git to cherry pick patches. And, we are wondering there if there's any ideas, if there's a better way to do this that would fill both the needs of developers and the needs of member developers.
How are we tracking what's not restricted?
Yeah, so on one hand we have Git repositories that are primarily used by the art team where we just do what developers regularly do and commit patches in Git repositories. And the other thing is that we essentially have a file that has a list of links to the Garrett repositories and it pulls the patches directly from there.
It seems like we could automate that in some way. It's like the kernel side, it's easy to track because it's just one repository. Here's the list of commits. But you need the list of commits against AOSP
right. And also sometimes patch is submitted to Linaro Gall because it's only for the hardware that is not supported upstream or so, and sometimes the patch is submitted to AOSP Gall because it should go upstream, but nobody is looking at it yet. So that's the issues we are facing there. Obviously, the best thing would be to just get everything upstream immediately, but that's not always working. Primarily it's two things. One is that for some patches, members are saying, no, we need some more benefits for membership, so we need to keep those members first. And for others, it's that we are trying to upstream them, but nobody is looking at them because probably the internal tree has moved on and the patches don't apply there.
So which components those patches are residing in now? Generally speaking, what kind of components we are speaking about?
Pretty much everywhere across the tree, from Bionic to System UI.
I think for System UI it's kind of difficult to get it in if it is not useful or kind of conforming to Google's sense of what is correct for the system, because it's applied to every device out there. I think for others it might be easier.
Does anybody in this room use the MLCR? That's Linaro's members confectionery release. Nobody? Not even you guys? Okay.
Okay, does anyone have anything else on upstreaming patches, maintaining out-of-tree patches? Next is the transition to Clang, but I think we'll skip over it because we are so far behind timing and we have the interesting art presentations coming up, unless someone has something really important they want to contribute to this discussion. No, it doesn't look like it. So next is Anton with an overview of VXLAN.
Hello everyone, my name is Anton Kiriouf and I'm a member of the Linaro Android runtime team, and I'm going to talk about VXO. So VXO is a programmatic assembler and disassembler. When most people hear about the assembler, they think about a program which takes a text file which contains assembly source code and transforms it into a binary. However, VXO is has been designed for the JIT compiler use case, and is meant to be embedded into other code and invoked from that code. It supports both AArch32 and AArch64, and supports both instruction sets which are in AArch32, that is A32 and T32. It's written in C++, it uses the modified BSD license, and it has several users. The major one is the Android runtime, but also QEMU, HHVM, and others. For AArch64, there is also a simulator and debugger, but this presentation is going to concentrate on AArch32. You see up there where you can obtain VXO, and last year in San Francisco there was another presentation about VXO which concentrated on AArch64. So if you're interested in that functionality, I suggest to refer to it. So let's start with the assembler, which is represented by the assembler class, which is this is the basic low-level interface, and it provides full control over code generation. For example, one can use the exact encoding that is used when generating instructions. It generates A32 code by default, but that can be controlled either when by the constructor of the assembler object or on the fly with some methods. What's useful to note is that it is possible to mix both A32 and T32 in the same generated code output. And I have a simple example. So on the left you can see the C code for the example, which is just a simple factorial. And on the right you can see the corresponding T32 code. So how does this look like with the VXL? So we define an assembler object, and as you can see, we set the instruction set that we are interested in, so T32 in this case. The assembler object has methods for every instruction. It's pretty straightforward. And for the labels that we had in the assembly code on the previous slide, we have a label class. The other thing that I should notice that after we are finished with using the assembler, we need to code the finalize code method so that the assembler can do some cleanup. Since the assembler class is, as I mentioned, a low-level interface and providing full control over the generated code, it has several limitations. With every assembler object, there is a code buffer object associated with which contains the output. But the assembler class doesn't, and this buffer has fixed size, and the assembler class doesn't do any checks, buffer overflow checks with this code buffer, because the intention is that the core is going to be responsible for that thing. Another limitation is that instructions, A32 and T32 instructions cannot encode all constant values. If an immediate is too large to be encoded by the assembler is just going to print an error message. Yeah, as I said, this is just the consequence of being a low-level interface, which provides exact control over the generated code. There is a macro assembler which builds up on the assembler. The interface is mostly the same, except that macro assembler methods are capitalized. But again, same thing, there is a method for every instruction that can be generated. The main advantage of the macro assembler is that it provides some extra features which make programming easier and safer. In particular, the nears for branch offsets, which cannot be encoded in the instructions, are automatically generated by the macro assembler. Also literal pools and several other things which I'm going to cover in the next slides. And this is, the macro assembler is the interface that I expect most people are going to use. So a particular example, so let's say that we want to do an addition with a very large constant. So we use, as you can see, a macro assembler method which is capitalized. And the macro assembler takes care of materializing the constant in a temporary register, which is R12 or IP as named by the ARM procedure call standard. And instead of generating a single instruction, it generates 3 instructions. So basically taking care of some work that we would do ourselves in the assembler class. The macro assembler also performs some very simple code optimizations. So as you can see in this example, we ask the assembler to generate the move instruction, again with a very large constant, which is not encodable as an immediate in the instruction. But the macro assembler detects that and replaces the move instruction with an MVM, which actually can encode the value that we are interested in. There are several other functionalities. For example, in compilers, frequently we need a temporary register for some temporary scratch register for some things. Since register allocation is a very expensive part of compilers, of the compiler pipeline, ideally we have a scratch register reserved by the calling convention to use for such things. And the use scratch register scope class provides a structured way to deal with using a scratch register. It uses standard C++ idiom. As you can see, you define an object, you scratch register scope, then from that object you acquire a temporary register, and you use it, and after the lifetime of the object is over, the temporary register will be given back to the macro assembler. The macro assembler has several pitfalls. Consider the following example, which actually is not real code. If you try to run this, to compile this, it's not going to work, but I'm just using it for illustrating my example. So we have an IT instruction and then followed by an addition. And the addition is done with a very large constant. So the macro assembler will generate the IT instruction and then a mov to materialize the, actually a couple of mofs to materialize the constant, and then finally the addition. But unfortunately, the IT instruction, which makes the execution condition, is going to refer only to the first instruction, which was definitely not the intention when we wrote that code. So that's why sometimes we actually want to have strict control over the generated code, even though we're using the macro assembler. And the assembler accurate scope class provides that functionality. So it prevents the macro assembler from emitting veneers and literal pools, which can also mess up with what we expect to find out in the generated code. And in fact, in situations like this, we actually should not use the macro assembler methods. We should use the assembler methods, the ones that are not capitalized. There is one slight usability issue, which is that the constructor of the assembler accurate scope class uses sizes in bytes instead of number of instructions. So here we have an example. Again, same C++ idiom. We declare an object. We say what is the maximum size in bytes that we expect to use. And then notice that we use the assembler methods, not the macro assembler, because they're not capitalized. And we generate exactly what we expect to do. So this is a table which summarizes the differences between the assembler and the macro assembler. Again, the assembler provides precise control over the generated code, while the macro assembler has a more relaxed approach to the same thing. But on the flip side, the macro assembler is more convenient to use, and it performs some simple optimizations. It's not a full-blown optimizing compiler. Let's move on to the disassembler, which is implemented in the disassembler class. One important thing to note about the disassembler is that it strives for strict ARM v8 compliance, so people who are used to ARM v7, the ARM v7 disassembly, might be slightly surprised by the output, such as some instruction suffixes and things like that. It's a little bit low level for most use cases, and this is especially the case if for T32 code and its variable length instructions. So that's why there is a wrapper class called the print disassembler, which provides a more convenient interface. And again, my expectation is that most applications are going to use it instead of the disassembler directly. It has methods for disassembling a whole buffer of instructions, but also some methods for disassembling a single instruction, which are particularly convenient for T32. So here we have an example. This is, contains the previous example that you saw several slides ago. We just declare a print disassembler object, and we call a method to disassemble the whole buffer. The assembler provides methods to obtain the buffer and the size in order to do that, and we get the output, which is on the right. The disassembler, print disassembler class, actually both of them provide a method to override the output, to customize the output. And this is done with the disassembler string class. It's used internally by the print disassembler and the disassembler. And every instruction is broken down into components such as registers, mem operands, and so on and so forth. The disassembler stream defines operators, stream operators for every component and their virtual functions. So they can be overridden. As a particular example, in the Android runtime, we use register 9R9 as a thread register. So when we disassemble, we want to print TR instead of R9, which makes the output a little bit more user-friendly. And that's done simply by declaring a class which inherits from the disassembler stream and overriding the method which prints the register names. So you can find more examples in the examples AR32 directory in the VXO source tree, and there's also some documentation, and a very good starting point is the getting started AR32 MD file in the doc directory. So now I'm going to say a few words about our usage of VXO in the Android runtime. So during the past several months, we have been working on changing the existing assembler and disassemblers in the Android runtime, which have been implemented by Google with VXO. And that led to safer and more extensible code base, safer because of some of the features that I have just shown you, and such as the use scratch register scope class, and more extensible code base because actually a majority of VXO is auto-generated from some internal ARM specifications, which makes it very easy to support future ISA extensions. And part of that automation is also there is much more extensive testing compared to the previous assemblers and disassemblers. And that's my presentation. Thank you for listening. If you have any questions.
Hello, everyone. My name is Artem Sirov, and I'm going to share the experience we gained during performance analysis of Android runtime. So my talk will be it's targeting people and engineers who wants to get acquainted with performance analysis of ART runtime, but also it might be interesting for experienced engineers, and they may find some interesting information here. So Android runtime is a managed runtime used by Java application and system services on Android. Currently, this year, Google has introduced a new version of Android 7 Nougat, and related to Android runtime, they introduced a hybrid mode. Probably you attended the speech of my colleague ArtJIT in Android N by Xueliang Zhang. So if you are interested in this, you could take a look in the internet. So my point is that what I will be talking today applies to Android 6 Marshmallow and to the ahead of time mode of Android 7, and also can be enhanced and improved to be used for JIT as well. So I'm a part of Linaro art team. We are working on Android runtime, improving the performance and stability, and our team consists of members and assignees from ARM, Spreadtrum, and MediaTek. So to measure performance, to track performance and analyze the performance degradations or improvement, we need benchmarks and tools to run. And we have a repository for it called R-Testing. So it has benchmarks and tools to run them. So the benchmarks, we believe that they are analyzable and flexible. So they have permissive license. They are command line ones, so they can be easily embedded into continuous integration systems. Also, they represent real-life programs, real-life code. We believe that they are very close to what Google uses when for benchmarking. So we have couple of well-known suites like Caffeine Mark, Benchmarks Game, some particular benchmarks like Richards, Delta Blue, some others, and also we have micro benchmarks. So whenever we add a feature to the compiler, we add a small benchmarks that test this exactly feature, and in this case it also can catch regressions if they happen. And our framework, it is very easy to use and very convenient to use. You can just run them in a single command line. You can run benchmarks both on target and host. It will provide you with the statistics and some statistical data, and also it have so-called perf tools, not the Linux perf tools, but our one. So I will be talking about them later. So this is how our development process looks. So, and this diagram shows the place of benchmarking and performance analysis. Whenever we deliver a patch, like functionality, we need to make sure that we improve the performance and don't bring any performance degradations. So this is the place where performance analysis occurs. But except this, we also continuously tracking the performance. We have special tools, art reports. The next slide I will show you. So our continuous integration system fetches the upstream AOSP tree and every 6 hours and run the benchmarks. Stores the data into a database and provides a number of fancy scripts and ways to visualize and analyze what was happening. This is how it looks. As you can see, you can choose. We run this on different configurations, like on the Nexus 6P, on Nexus 9, and on when we run it on Nexus 6P, we run the benchmarks separately on A57, A53s. So you could, when you enter this site, this is a web page actually, so you could choose the configuration you're interested in, and you can specify the benchmark suite or a particular benchmarks to see how the performance progressed and during the time. So on this diagram, you see we've chosen a loop atom benchmark from Caffeine Mark, and we see that the performance significantly increased. So the lower the better. It's that time. So let's try to analyze what happened. So using this web page, we can understand like the 2 points before and after. Between these points, something happened, and performance increased. So for these service art reports use so-called build scripts. So these are the automated scripts that enables automated process to run benchmarks, building, configuring device, running them. So they are again quite easy to use. So one of the main advantages is that these scripts are used. They can be used both locally and in the automation. So whenever we see degradations or improvement on from our automation, we can exactly reproduce the same things, the same behavior locally. So these scripts have a couple of features. One of them is Android root. So this is kind of a CH root feature. So it uses, instead of using the system binaries and libraries from the system path, it uses a custom path for it. So we use this because the upstream AOSP tree sometimes is broken, and you cannot just sometimes it cannot boot to GUI. So this feature provides make us possible to run the benchmarks every time and not be dependent on the failures and errors on AOSP upstream. So also before we run the benchmarks, we configure the device. So we pin the frequency, not to the maximal value, but to some reasonable one, not to cause overheating. We also pin the CPU we're interested in, let's say A53 or A57 on the Nexus 6P, and then we run benchmarks. So after we have understood which two points we are interested in, like before and after, right? We can ask our automation to provide all the data, to fetch the data from the database, the raw data for the benchmarks, and it can show you the difference, filter them by, let's say, by the percent of degradation or by configuration. And after you can download this data and manually check the data on your desktop. And here, how the summary of the benchmark of the performance statistics looks. So we see like the negative number are better, so the time has been decreased. So we can see the benchmark suites we have, and the difference, Gemin difference, and the STDEF. So yeah, in this case, I particularly put caffeine loop atom benchmarks, and it shows that the time has shrinked by 24% between points R and B, let's say before and after. So yeah, we have just justified this fact, and our task is to investigate what is the reason for this performance difference. So yeah, this is maybe the naive but generic algorithm how one should perform performance analysis. So one of the main terms in the field of performance analysis, the hotspots. So the hotspots are the sections of code that get most of execution time, and typically, and this is proven, like we have justified it by during our experience, that the hotspots determine the overall performance. There are often there are a few of them, and they are our target. So the naive algorithm is the first find hotspots, then analyze hotspots. Probably after this you will understand what's going on. So when profiling can help us finding hotspots. So the level of profiling can be different. It could be either method level, loop level, or instruction level. And after we identified the hotspots, we will analyze this, and we could look at the source code, the difference in source in the source code. No, it's not. In the difference in binary code in IR, and we could use some tools to help us. So we have these tools in our testing repository. So they are based on Linux perf tools. They implement wrappers around this. They do profiling. They identify the hotspots. They provide us a CFG file, so that special special to art file that have IR intermediate representation, assembly, some other information. Also, these scripts collects statistical data for perf events. Yeah, this can be done in one click, in one command line. So yes, look at this diagram. So this diagram has been retrieved from perf report. So, and here we can see that the top one in the list is a function, a method from the benchmark file itself. So it's the Java code, and it's about 90% of all the time. So probably we are interested in this particular method, and we will analyze it. So here we could also see some kernel addresses, kernel methods methods from Art itself, from the runtime. So, but as we are interested in the code generation, mostly interested in the development of Art itself and not the kernel, we are interested in Java methods. The CFG file, as I said, it contains a control flow graph of the program, of the benchmarks, intermediate representation, and assembly. So more than that, CFG file contains this information for all the methods in the APK or a DEX file, and for each method, like here, look. This is loop method execute. You could it stores this information after each compiler phase or pass, so you could understand what is going on between the compiler phases. And yeah, a C1 visualizer is a very convenient tool to look at this file. So this is how it looks. On the left, you could see the source of the benchmark written in Java. In the middle, it is a CFG a control flow graph, and to the right, it is the result of the output of a perf annotate. So here you could see from the left, you could see that the function has loops, nested loop. Then it simply reflects in the control flow graph, and a perf report. A perf annotate shows us that actually the inner loop is a hotspot. So let's continue and look at the basics blocks of the inner loop. So this is like the rough idea how this IR looks. Maybe it's quite difficult to read, but yeah, I already know this. But that we are interested in these two H instructions. H instruction is high level intermediate representation instructions. So to the left, what was before, and to the right, what was after. After the. So the right one represents the performance improvement. So not going into details, you see that there is less instructions, less assembly instructions. I don't think that we have time to go into details right now. So yeah, at this point, it's already clear what's the difference, what's the reason. So, but quite often the performance investigation could stop here because it's already clear. But if not, we can continue. As I said, our framework provides some interfaces and some wrappers to perf tools. So it actually collects, it runs the benchmark and collects every perf event from the list, from the configure file. So after this, we could form a table containing perf counters for 2 runs and to compare them. So here, like IPC is the most known ratio. It is instructions per cycle, and it reflects performance. The bigger, the better performance. So we could see that the performance actually APC has increased from significantly, and this proves that actually this justifies the performance difference. But also, what we could see from here is that this 0xE5 counter that actually tells us that previously, before the load store instructions were waiting for the address calculation. If you could see here, the load instructions depends on the add, and add this complex instruction. So, and this counter has been significantly decreased. This event is much less frequent. Yeah, here I used this. So I call this EPI. So event per 1,000 instructions. And if you sort the table by this parameter, you could understand the importance, like the impact of this particular event. So yeah. Also, Another convenient tool for performance analysis is DS5 Streamline Performance Analyzer. So it is a part of ARM DS5 Streamline, of ARM DS5 tool. So it also supports PMU counters, performance monitor unit counters analysis, but it has a fancy feature of timeline. I will show you in the next slide. And this actually, this tool is a system-wide performance analysis. So you could observe all the threads, all different processes, how they interact. And yeah, it supports both Linux and Android. You could find a tutorial how you could use it on Android. And here how it looks. So here, maybe it's a little bit small, but you see this, the fancy feature that I personally like is that you can have like custom graphs here. So you see there is instructions executed, it is red, and clocks, it's blue. So you could actually specify an equation, like you see instructions executed divided by clock cycles. So you could easily customize them and visualize, well, let's say, whatever you are interested in. Yes, so some useful links, you could follow them and read information. Yeah, that's probably it. So, any questions? I understand everybody is hungry and thinking about lunch, but yeah. If you have any questions, you could find us, Linaro team or me personally, in LMG hacking room. You're welcome to come and ask any questions you have. So thanks.